think of combines, all of these things on the heads on them, they all work off of this principle. So there's a lot of this out there. Now, I'll kind of put this on the overhead so you can see the different devices. And then I'll pass them around. So here's the color. Kind of see that keyway right there in the top? Okay, now I have two items right here I'm also going to show you. Because I got a couple seats. I don't have the right one to fit here. This is a key. It's basically a rectangular chunk of metal. This is for a fairly large one. Here's a small one, right here. Okay. And again, it's a rectangle. So what will happen is we'll slide this on the shaft, and then these pieces go right in here. Now where it will go halfway in the shaft, halfway in the collar. As this thing turns and it gets caught, we want this piece right here to break. We want this key to break to protect the shaft. That's what we use them for. It's a connection device, and it's also to protect our equipment. So let me just pass these things around. They're kind of heavy, so be a little careful with them. The shaft is heavy. I got to get a small one. But here's the collar shaft, and then here's the two keyways. And I'll just kind of pass them around so you can kind of see how they work. It's pretty obvious once you put them together. You'll want to line up this end. Can you kind of see that rectangle in there on that end? Okay. That lines up with the rectangle here on this one.
Why is that so expensive, the precision of that?
Yeah, it's usually a stainless. It's expensive piece of metal, and to get these things straight, it is very hard to do. Okay? Very hard to do. So we'll just pass this guy around.
Huh.
While we're passing stuff around, let's pass one other thing around. I did pull this out too. This guy right here is a countersink bit. So you can see how it works. It's basically machined to an angle here. You'll see if you look on it. There will be some writing on it. So this guy right here, it is a 3/8 by 82 degree countersink bit. Okay. And so this is how we make those countersink holes. So I'll go ahead and pass that one around. Also, if you've never seen one of those. All right, now let's get to the dimensioning. Since we have this device that's going to be used quite often, they are dimensioned specifically so that the key will work. Now, when we put those keys in, you just get a little rectangular chunk of metal, and we hammer them in. It's got to be a friction fit when they come in. But we need to make sure we got enough room to get them in. So they are dimensioned a specific way. Now, on this one, notice as they're done, I don't like one thing here. That should really be right there, and that should not be there, okay, for ANSI standards. So you're going to do the diameter of your shaft. This is the full diameter. Then you give the width of the key, and then you give the dimension from the bottom of the shaft to the top or the bottom of the seat. They then have to figure out what this missing dimension is. Now, you can't dimension from the top down. Why? The top's not there. That's why we come from the bottom of the shaft to the bottom of the seat. That ensures that the key will fit in this side. When you come to the key way, again, give the width, give the diameter of the hole. Again, this should be dimensioned like such. Then you give the bottom to the top, because you're in the collar at this point. Again, we can't give this dimension because that isn't there for them to measure from. So when you get a keyway or key seat, it needs to be dimensioned in this fashion. Yes, Becca?
So if the keyway has like a variation, just the keyway, like not any other dimensions, would you put that in the notes? Be like keyway has a variation of 0.02 plus or minus?
A tolerance, you mean?
Yeah.
No, not really. These are manufactured devices. You buy them as a general rule. We don't make them.
Mm-hmm.
Okay, and every mine I worked at, we'd go to the warehouse and there would be bins of these things. Okay, where we had purchased them, they're just sitting in there, kind of like you'd go grab a bolt out of a bolt bin.
Uh-huh.
Okay, and we'd just go look for the right size of them. So they do have a tolerance when they're built. They would go to the general tolerance of the drawing. Keep in mind, we want this thing a little bit too big, because we've got to hammer this in. Remember, these things are turning. These are shafts for the most part. And I mean, even your car, which has a fairly small one of these in it, that's coming off the power portion of your engine, that thing at idle is turning what, 1,000 times a minute?
Mm-hmm.
And then our new cars that are getting more fine-tuned, it's not rare for a car now to be able to hit 6,000 RPMs and not redline. So that's pretty fast, and that's for a car, which isn't really that fast of an idle. Okay, certainly nothing like a pump. It's not rare for pumps to move in the 50,000 RPM mode. So be that as it may, when you're doing this, don't worry about the seat per se on this, because we're going to use a standard one for it. This is for the shaft and the collar. So this is kind of the tricky one, coming from the bottom up. Keep in mind, when you're doing the key, how much of this probably sits down in the bottom part? Most keys are square. You can get rectangular ones. Yes, Deb?
I've seen them like a half moon.
Yeah, this one would be 1/4 wide by how deep? Well, you figure this right here is an 1/8, right? Difference? Half of it's going to sit down on the bottom. This key right here is going to be a 1/8 by 1/4. That's the key, or the little metal piece that's going to fit in there. Because you're going to put an 1/8 of it right here, right? Then an 1/8 is going to fit in the shaft, as a general rule. Same with this one. This is the same way. So it's 1/4, and this one's an 1/8 inch wide, but 1/4 inch deep. Because there's an 1/8 difference right here, right? So that's an 1/8. The other 1/8, the key, if I was to draw it, is going to sit right there to join the two devices. Now we have a bunch of different types of keys. We got Woodruff keys, which actually that shaft I'm passing around is actually machined for a Woodruff key. That goes in the internal. We'll cover more of those when we do drafting or draft 150 in the summer, because mostly this is a mechanical device. We cover the different types of keys. All right, the last one, irregular curves. Irregular curves, let's just kind of go, let's go to page 827, and then I'm going to bump back to chapter 10 also on this. What happens when we have irregular curves? So figure 17, 18. On page 827. When we have curves that do not follow a set pattern, okay, by a set sweep, I'm talking about diameter or radius, a constant radius. When we have curves that don't follow a constant radius, we call them irregular curves. We need to dimension them with x and y dimensions, or offsets. So in this instance, our datum is this line right here, or this point. We are then giving certain points along the curve. When you get to those datum points, like here, here, and here, we need to give the linear dimension from our datum on that. Okay, so for those that are doing is they're just coming in and saying, you know what, I'm going to pick a point right there, right there, right there. Now I'm going to give the deviation from it. So in the x direction, I'm going 23. In the y direction, I'm going 2.5. This shows the obliquing extension lines, which you can do. Most of the time, these will be pulled straight. They just couldn't get them on here. So then I would give the xy offset for that point, xy offset for that point. Don't expect this curve to be built any better than the datum points you give them. And then they will try and fit a tangent curve to that, just like you would try to when you drew it. They don't have a P-line, but they do have extensive French curves, and they'll get it fairly close. If you need to tighten the curve up and it's real important that it's exact, I'm not going to go to chapter 10, but you probably remember this figure. I just sketched it. But if I needed to be real exact, I would do it kind of like this, where I would give them as many datum points as they need to accurately build the curve. And then I give the XY offsets for all of those. And yeah, we can get into extensive dimensioning on these. But if that's what it takes to get the part built and to do the job the part is designed to do, that's what we've got to do.
So in the drawing before, your oblique dimensions, are they supposed to be at a certain angle?
No,
No, just
they can
whatever.
be at any angle, just as they need to all be the same angle.
Okay.
Yeah. Okay, so irregular curves. Locate datum points, probably the same way you drew it, and then locate those datum points along the curve. I'm going to do a little exercise here.
Hey. This doesn't mean this. Copy. Thank you. Ooh, yay. Three-dimensional.
Okay, I want to do a little class dimensioning exercise. So what I'm going to do is, I'm going to give you 10 minutes. I would like you to sketch how you would dimension this object, and then take a break. Hey, we'll pick back up at the top of the hour. And then what's going to happen is I'm going to call on individuals in here and say, can you locate this item? And then you would come up on the board, we're going to leave it here, you're going to locate it, you're going to size it, whatever the case might be, and then we're going to discuss it as a class and say, well, would that go here, would it go here, would it go there? Keep in mind, by any stretch of the imagination, I don't want to humiliate you or anything. This is a discussion. Okay? So go ahead and think about it, sketch your dimensions, and then we'll come back together as a group and see how we would dimension this object.